Relating star cluster formation in cosmological simulation.
All right. Let me change topic from observation to simulations. Okay, my name is Hui Li. I'm a third-year graduate student in University of Michigan. So currently I'm working with Oleg Gnadin on the star cluster formation using cosmological simulations. So first I'll try to use a couple minutes to convince you guys that star clusters are very important. So there's one example for the global clusters. Global clusters are one of the oldest objects in the universe. And so currently, recently the ACS World Cluster Survey has revealed a multi-model metallicity distribution of global clusters within most of their massive galaxies in the Virgo cluster. And the origin of this bimodal shape of this metallicity is still under hot debate. And last year, Oleg and I started a semi-analytical model try to tackle this problem, and we use this. We built this semi-analytical model based on the Millennium 2 simulation database. And the main assumption of this semi-analytical model is that these massive star clusters can only be formed during major merger. And with this assumption, we can reproduce the this bimodal shape of the metallicity distribution, as well as the mass distribution of global clusters with a wide range of masses. And we also find that the distribution of these global clusters in the age metallicity plane is very sensitive to the merger history, as well as this chemical enrichment history of the host galaxy. So the metallicity distribution alone can provide some fossil evidence on the mass assembly and the chemical enrichment history of the host galaxy. And on the other hand, there are some very interesting observations on the young massive star clusters. So one interesting fact is that when people observe the star formation rate, star formation region, especially the massive star cluster formation region, people find the cluster formation timescale as well as the molecular cloud disruption timescale is very short. They are as short as only a couple of free-fall timescale. And this suggests a very strong feedback from young stars. So if we see this plot, so the timescale of this process can even be can as short as about 5 million years. This is even before the first supernovae can put the energy onto the star formation region. So these observations can give a strong constraint on the star formation and the feedback physics that we put in the cosmological simulations. So in order to simulate the star cluster formation, we currently use a density refinement tree code, the so-called ART code, initially developed by Andrew Krebsov. And I don't want to go through the details of this simulation, but I just want to highlight that our code have recently implemented a full 3D radiative transfer together with a non-equilibrium chemical network that can deal with the runtime treatment of the molecular hydrogen formation and destruction. And this gives us an opportunity to better estimate the molecular component of the simulation so that we can build our cluster on this molecular components. So I'll briefly mention our continuous cluster formation recipe. So at first, it's just like typical method. We see the cluster particle within a certain cell when the cell is cold and dense enough. And then, rather than creating star cluster particles at each time step, we instead grow the active particle by drawing the gas within a sphere of a fixed physical size, which can represent roughly the size of the giant molecular cloud. And we grow the particle until the feedback starts to operate and the star particle start to expel the gas and disrupt this host giant molecular cloud. And then the cluster can stop growing self-consistently, and then we turn off this active particle into inactive. And then we run a set of test cosmological simulations from the initial condition that can turn a Milky Way-sized galaxy at redshift 0. And this is the run that stops at redshift 4. And these two plots are the projected density plots. And this one I overplot the young star clusters that has age is smaller than 15 million years. And what we find is that these young star clusters follows well with the density structure of the host galaxy. And and in this plot, I show these blue dots represent the massive cluster that has mass more than 10 to the 5 solar masses. And these clusters are formed mainly at the peak places of the main halo as well as the satellite galaxies. And but I don't think you can see clearly, but there are some dots in this less dense area. And these are due to the fact of the dynamic interaction between these massive clusters and the galaxy components. And we also investigate the star cluster formation history. Okay, the star cluster formation history, and the blue dots represent each blue dots represent the star clusters formed at certain cosmic time with certain initial masses. And what we find is I also overplot the dark matter halo merger ratio history at different time scale, at different cosmic time. So what we find is that most massive star clusters are preferentially formed when there's a high merger ratio. And this is also consistent with the assumption that I mentioned in our semi-elliptic model in the first slide. And so another observational fact of the cluster of the young star clusters is the cluster initial mass function. And recently, people observed the young star clusters within in different nearby galaxies, and they all found a universal shape of this cluster initial mass function. They are power law shape with different truncated mass. And in our simulation, we also found a similar cluster initial mass function with the slope is very close to -2, which is consistent with observation. And we also split the initial mass function for the cases of the merger event and non-merger event. And we find that during the merger event, the initial mass function has much higher truncated mass than the non-merger cases. And also, after a closer examination of this phenomena, we find that there's a strong correlation between the star formation rate, the instantaneous star formation rate at certain epoch, with the maximum mass of the cluster that formed in that epoch. And this is also consistent with recent observation by Adamo et al., which shows there's a correlation between the star formation rate and the V-band magnitude of the brightest star clusters in different galaxies. And but all of these results are very preliminary, and that's all I can provide. So I'll leave the summary here. Okay, thank you very much.
Joel and then Mark.
You started by showing the color bimodality or multimodality of
Yes.
globular clusters. And you said that could be explained somehow as a consequence of globular cluster formation in galaxy collisions.
Yes.
But I never heard the connection between the color bimodality and the galaxy collision idea. Could you elaborate?
Oh yeah. So first, this color bimodality can be translated to the metallicity bimodality if you use the relationship between the color and the metallicity. And then the problem becomes how does this, what's the origin of this metallicity bimodality? And what we find, if we use the assumption that the major merger, only the major merger can trigger the formation of star clusters, we'll find most of these red peaks are formed when there's a collective of major merger in the early universe. And because the major merger events are more frequently in the early universe, then they create a whole bunch of different, a large number of star clusters that in the early universe that create this peak of metal poor population. And then as the major merger events become more rare and rare, and then there's a drop. But in the late universe, then there might be a couple of major merger events happen, and these major merger, although they are rare, but they contain more masses, and these major merger alone can create this more metal-rich populations.
Do you think that the red and blue globules of the Milky Way formed by major mergers? Is that consistent with other facts about it?
Yeah, and so before our work, Sasha Muratov and Oleg did similar work using the semi-analytical model. They specifically try to explain the global cluster populations of our Milky Way. So they also use this assumption, and they can also reproduce the bimodality of our Milky Way global cluster population.
Hi. So I wanted to ask about the truncation mass. As I'm sure you're aware, there's sort of a holy war in the literature as to whether there really is one. And the problem is that it's always right at the edge of statistical significance because it's right where, so it's hard to distinguish whether there's truly a truncation or it's just a size of sample effect and it's a pure power law.
Yeah.
So it occurred to me, in your simulations, you've got vastly better statistics than the observers are ever going to get. So have you done the test in your simulations of, say, splitting it into periods of high star formation rate and low star formation rate, taking the clusters formed in each of these two bins, and then you could actually distinguish between it's a pure power law and it's a size of sample effect that you get more massive clusters at higher star formation rate, or there's a physical truncation. Have you done that test?
Yeah, that's a very good question. We did. For the major merger cases, we do find a truncated mass. We use we first fit this initial mass function with a pure power law distribution, and then we fit this with a power law distribution with truncated mass, and we compare the maximum likelihood of these two fits, and we use the likelihood ratio test to test whether there really exists a truncated mass, and we do find in the major merger cases, but we do not find in the no major merger cases. But another case is for the non-merger cases, the number of the star clusters is smaller, so it is not. It is much harder to draw, the significance of the statistics. So we are still investigating into that. But that's a very good question.
Quick question.
Very quick question. So the image you have shown with your gas disk, cosmological gas disk,
Yes.
looks to me very smooth. And so what controls the mass? How much mass is acquired by the globular cluster particle, the star cluster particle? Is it the time the particle spent before feedback, given the surface density you have, or is it because I don't see how you can get the mass from fragmentation physics, or you see what I mean? So in nature, star clusters form because they fragment, they isolate from the surrounding. Here, what happens here exactly?
I think this is a kind of just after this is kind of a quiescent period just after a major merger happened. So these just checking the simulation. These are the kind of the tidal effect of the interaction, and still I can't say exactly why don't we have this kind of segmentation in this sphere arm, but using our algorithm, we do find that the star clusters can grow to, for example, more than 10 to the 6 solar masses when there's a major merger. But in this case, in this kind of a quiescent case, the star cluster can only have, for example, mass smaller than 10 to the 5.
Okay, it's coffee time, and let's